Now that we know all of the quantum mechanical rules for orbitals, and we know how having more than one electron changes the energy of orbitals, and we know about Pauli exclusion principle so that we know that each orbital may contain at most 2 electrons, we're now in a position to describe in detail where the electrons are in each atom. And the way that we're going to do this description is by using things called electron configurations and orbital diagrams. You can read about this in section 8 of chapter 6. Let's start with electron configurations. An electron configuration is just a special way of specifying the location of all electrons in an atom in terms of the subshells, which subshells are occupied by how many electrons. The rules that we're going to follow. First of all, we're going to specify each occupied atomic subshell in order of increasing energy. For each subshell that is occupied, we're going to indicate the number of electrons in that subshell with a superscript, a number indicating the number of electrons. When we use these superscripts, a 1 superscript is never assumed, so you have to show a 1 explicitly. Again, these superscripts are a count of electrons. They're not actual algebraic powers of any kind. They're literally just the count of electrons contained in a given subshell. You'll see examples, don't worry. And then finally, just because I often see exceptions to this when students are learning this material, it's all one big string of characters indicating the subshells with superscripts indicating the number of electrons in each subshell. There's no punctuation, there's no spaces, there's no commas, nothing like that. Now what we're going to be doing are things called ground state electron configurations, which is just the arrangement of the electrons in the atom in its lowest possible energy arrangement. And this is almost exclusively what we're going to be talking about this quarter. Occasionally, there will be a need to describe the arrangement of electrons in an excited state atom, and we'll look at that later. For now, let's just learn the basics of doing the ground state electron configuration. So whenever I talk about electron configurations, unless I specify excited state, assume it's the ground state or lowest energy arrangement of electrons among the subshells. The other way that we can specify where the electrons are in an atom is with a device called an orbital diagram. It contains a little bit more information than an electron configuration. So what it is an explicit listing of up spins and down spins represented by up arrows and down arrows in a system using the following conventions. We're going to use boxes to represent orbitals. I should tell you, if you look up orbital diagrams on the internet and look at different videos, there are different ways of doing this. In our class, you must use a box. Even though there are other ways of doing it, that's the method for our class. Any other method will be marked wrong. If a subshell contains any electrons, then all of the degenerate orbitals for that subshell must be shown in the orbital diagram. We'll see implications of that in just a moment. And the way that we represent degenerate orbitals is, again, this is just a convention, but it's important to understand. We're going to show the degenerate 3p orbitals, they're all the same energy, as sharing sides, by which I mean this is a common side of both this orbital and this orbital. So if you have spaces between the boxes, then you're implying that those are not degenerate orbitals, so don't do this. All right? So let's just work out some examples, and hopefully this will help clarify what we mean by electron configurations and orbital diagrams. So over on the left-hand side, I've just shown an energy scale just to remind you that the energy goes, we want to fill this orbital, then fill this one. In order to get the lowest possible energy, we fill them starting with the lowest possible energy until we run out of electrons. So for example, for hydrogen, the first thing to do when writing an electron configuration is to figure out how many electrons are in this species. Hydrogen has 1 electron, so we only have to show 1 electron. We put it in the lowest energy subshell, so the ground state electron configuration is red 1s1, meaning there's 1 electron in the 1s subshell. And the way we would draw this in an orbital diagram, we draw a single box label it as 1s, and then we draw in that a single up arrow, indicating there's only one electron in that box. Okay. For helium, we know there's 2 electrons. We've got to show all of the electrons. I can put 1 electron in the 1s, and as long as I change the spin on the second electron, I can put the second electron in the 1s. So this is a 1s2 electron configuration. If I were to draw the orbital diagram, again, I have a 1s box. I'm going to keep the 1s label common for both of them just to save space. I have an up arrow and a down arrow. They have to have opposite spins, and that's one of the points of the orbital diagram, is to show how the spins align. Beryllium. See, beryllium has 4 electrons. Look that up on a periodic table if you have to. So the electrons are going to go 2 electrons in the 1s, then 2 more in the 2s, the way we represent that. 1s2, 2s2. I have a box for the 1s, a separate box for the 2s. I'll label that 2s. And then when I draw in my arrows, there's up, oops, I wanted them to be green just to look different. Up and down, and there's my, and now I've destroyed my box. Well, you get the idea. Spin paired electrons, that's what we call this. Spin paired electrons in the 1s orbital and spin paired electrons in the 2s orbital. When we get to boron, now we've got 5 electrons. So 1s2, 2s2. That's as many electrons as the 2s subshell can hold. So we go to the next subshell, 2p1. We're going to draw the orbital diagram. Separate box for the 1s, separate box for the 2s. 3 connected boxes for the 2p. And then fill in the arrows, 1, 2, 3, 4, 5. That's supposed to be an up arrow. For carbon, now we get up to 6 electrons. So 1s2, 2s2, 2p2. I'm going to draw the same boxes, and I'll just keep common labels with the example above. Now I've got 2 possible ways of doing this. If you think about this, right, so if I put in my arrows, I could put them in spin paired. They have to be spin paired in the 1s and the 2s. I could put them spin paired in the 2p like that, or I could put them like that. Which one should it be for the lowest energy? Well, we have a rule for this based on experimental evidence. It's called Hund's rule. This is a rule about getting the lowest energy arrangement, and it says that the lowest energy configuration of electrons in a set of degenerate orbitals maximizes the number of electrons with the same spin. Or in other words, we want to maximize the total spin when we add the spins of all the electrons together. This has the effect equivalent of saying the electrons spread out as much as possible to be among the degenerate orbitals and point in the same way, so that the ground state carbon orbital diagram will have a box for the 1s, a separate box because it's a separate energy for the 2s, 3 connected boxes for the 2p. Remember, we have to show all 3 orbitals, even if only one of them is occupied. And then we'll draw in the arrows, and according to Hund's rule, it's lower energy if those 2 electrons spread out among degenerate orbitals. Now, as we write electron configurations for bigger and bigger atoms, we have to represent a lot of electrons, and so it's handy to have sort of a short form or a shortcut electron configuration. And this shortcut is going to be based on the fact that noble gases are particularly stable. So if we look at the electron configurations of noble gases, and then we use that as a basis for providing a shortcut, we can use that to use a closest noble gas to represent its equivalent electron configuration. Let me show you how this works with a simple example. Sodium, if we follow the rules that we've been using so far, the electron configuration you should come up with is this: 1s2, 2s2, 2p6. Notice, by the way, that the 6 there means 6 electrons in the 2p subshell. It doesn't mean 6 electrons in an orbital. There's 3 orbitals in the subshell, and they're all filled. 3s1. Here's the point of the shortcut. This part of the electron configuration looks exactly like the electron configuration of neon. So we take neon and replace that part of the electron configuration to give our short form. And there's the short form version of the electron configuration, and it's just a simpler way of doing it. And anytime I ask for an electron configuration, unless I specify that you must give me the long form, you can use either the long or the short form, whichever you find more convenient. So now if we just compare these electron configurations in short form for lithium, sodium, and potassium, we notice something interesting. If we use this short form, all of the outer electron configurations outside of that square bracket bit look kind of the same. 2s1, 3s1, 4s1. This is really the key to the chemical similarity between elements in the same group on the periodic table. Let's just define a few terms so that we can refer to this effect more easily. So the first term I want to define is core electrons. Those are electrons that would be in the electron configuration of the noble gas part in the short form electron configuration. Core electrons never play any role in chemistry. They're not involved in forming bonds. They're not involved in forming ions. They're an important part of the atom, but they're not involved in chemistry. Chemistry, it turns out, is determined by electrons that we call valence electrons. Valence electrons are the electrons in the outermost s and p subshells. By outermost, I mean s and p subshells that are not in the core. And valence electrons are the electrons involved in any sort of chemical bonding. Doesn't matter what kind, ionic bonding, covalent bonding, all bonding is determined by valence electrons. So knowing about valence electrons, being able to count valence electrons in an atom, is incredibly important to understand the underlying chemical principles. So valence electrons are extremely important. All right, now using the rules that we have for electron configurations, it turns out there are some exceptions to those rules on the periodic table, elements that don't follow the rules that we talked about. We're not going to worry about very many of these. There's about 18 or so, and the point here is not to memorize electron configurations, but rather to understand the general trend that predicts electron configurations. As long as you can use the trend in the way that we've described, you're going to be in good shape in terms of answering homework or test problems. I am going to ask you to know the following 5 exceptions. There's not very many, and I'll give you a little way of remembering them. It turns out that there is a special stability associated with either having an exactly filled subshell or an exactly half-filled subshell. And this is so pronounced in the D subshell, where there's a lot of electrons, that it sometimes changes the order in which electrons fill subshells. So these are the 5 exceptions that I want you to know. Chromium, molybdenum, copper, silver, and gold all promote one outermost s electron in order to achieve this energetic stability associated with a half or completely filled D subshell. And the easy way to remember these 5 exceptions is to look at a periodic table and see where they are on that table, and I'll show you on the next slide. So again, on this slide, I'm just going to show you where those exceptions to the ordering rule for electron configurations are. We said chromium and molybdenum, they're right here. They're in column 4, If they took one of these s electrons and promoted it up, they would end up in an exactly half-filled subshell. And likewise, copper, silver, and gold are in column 9 of the D block here. And by adding one electron, they would have a completely filled subshell. Notice that tungsten doesn't do this for reasons that we don't want to get into. But this is a fairly easy way of remembering those 5 exceptions.